that's loud.
Yeah.
So, good morning, everyone. You made the way back here. All right, that's great. We got a full packed program today, so we'll start right away. And there's 3 paper sessions actually coming up today. The most important part is also lunch and the boat tour and more. And there's a small opening remark I want to make. And in case you've been at HPG or like registered for HPG last year, there was the option to collect or to get a wooden canal box, right? And Andrew has been working overtime whole year, and he cannot see the canal box anymore because he had to make so much of them, so he wants to get rid of them. So please, if you still owe one, please go down to the registration desk today and pick it up, so he actually can do something else for a change. Right, so getting into the paper sessions, we have 4 great papers coming up. It's on appearance and modeling. And the first paper is presented by Thomas Delio, and it's on real-time rendering of Glinty appearances. So have fun.
Thanks. All right. Today I'm going to talk about real-time rendering of Glinty appearances. But first off, what are glints exactly? I've selected a few examples here. Glints come from a distribution of very specular microfacets on a surface, and it is a mesoscopic phenomenon, something that happens in between the microscopic and the macroscopic. In this work, we bring needed improvements on key areas of real-time glint rendering, and the question we asked ourselves was, what do we need to do for games to finally start using this stuff? And so we built our entire project with this in mind. So as I was saying, glints happen in between the microscopic and the macroscopic scale. The microscopic here is on the left. It's when we can see the individual microfacets on the surface. The macroscopic is on the right. It's when we zoom out far enough for the individual orientations of the microfacets to converge. And the mesoscopic is in the middle, when we can't see the microfacets anymore, but their individual orientations are still statistically important in the result. In rendering, the microscopic is typically handled by a normal map, and the macroscopic by a continuous BRDF model, thanks to the NDF, the normal distribution function. But what can we use for the mesoscopic scale? In the world of offline rendering, we can use the method of Jacob and others. This paper's contribution is a mesoscopic microfacet model, which is both simple and able to reproduce the effect of glints with a strong spatial and angular variation. Because glints can be summarized like this visually. It's a variation of the reflectance along the surface, as we see in the picture, but also a variation in movement when the camera or the light moves. Their method simulates a distribution of a finite number of microfacets on the surface, each with a 2D position and a 2D orientation, and they replace the NDF by a counting process in those 4 dimensions. For a given pixel footprint, they go through all the microfacets and count how many fall within it, and among them, they count how many reflect the incident light towards the camera. And in this model, the microfacet's reflectance is binary. Either it reflects light in the right direction or not at all. This counting process aims at computing the ratio between the amount of reflecting microfacets and the total amount, and roughly speaking, it's with this that they can replace the continuous NDF. It gives them a stochastic NDF instead, which depends on the position of the pixel footprint. But to evaluate it, they need to explicitly go through every microfacet of the predefined distribution. That's a very expensive 4D search, and thus this method is reserved for offline rendering. So let's talk about real-time now. There are a few methods which aim at offering a real-time mesoscopic microfacet model, both physically based and sticking to the constraints of real-time rendering. And the method of Zur and Kaplinen here just happens to be an approximation of Jacob's method we just saw. So how did they manage that? With a few clever compromises. First, they chose to constrain the spatial distribution of the microfacets within a grid with only 1 microfacet per cell, and this allows counting the amount of facets within the footprint analytically. It's simply proportional to the area of the footprint on the surface and the microfacet density parameter. And secondly, they chose to free themselves of a unique microfacet distribution predefined on the entire surface and for all possible viewpoints. Instead, they decide to assign a random number theta to each pixel footprint P, and to define for this footprint its own procedural distribution of microfacet orientations. And finally, they chose to keep the binary microfacet from Jacob's model, which are either reflective, either not. And thanks to this, they are able to directly evaluate the amount of reflecting facets with a binomial law. And for n Bernoulli trials with a probability p of reflecting light. More recently, we also have the paper from Shermain and others. They based their method on the same compromises as that of Zer and Kaplinen to also target real-time performance. But in their case, the last building block is changed. Instead of using a binary microfacet reflectance counted with a binomial, they propose a more physically based model with a set of real pre-calculated multi-scale Glinty NDFs. In practice, these two methods are both based on the same three fundamental building blocks, which are required by the compromises made to achieve real-time performance. First, they need a level of detail structure. The reason for that is that we can't actually just easily assign a random number to the pixel's footprint. Instead, what we need is a random numbers which are anchored to the surface of the object, so that they are stable both spatially and temporally on the object's surface. So what we do is simply distribute the random numbers on the vertices of a virtual grid defined on the surface. And to allow dynamic adaptation to the size of the footprint, we also introduce a structure with discrete levels of detail. And with this, we get a set of virtual grids, all anchored on the surface, which allow us to evaluate the Glinty NDF with random numbers, while always sticking close to the scale of the pixel footprint. But to do this, it of course implies being able to interpolate between two different grids at once. And that will be the second fundamental building block we'll talk about. And finally, the last building block is the evaluation of the Glinty NDF itself from the random numbers assigned to the vertices of these grids. And this is where the two methods differ. Now, in practice, if we try to use these two methods in simple cases, we quickly realize that they both have important and similar problems, all linked to these three building blocks. First, their level of detail structure can only adapt itself to the isotropic size of the pixel footprint. And for anisotropic footprints, the only solution is to manually evaluate many more samples on the grid. And that's very expensive in real rendering scenarios, where anisotropy is variable and everywhere. Secondly, we quickly observe blending artifacts visible between the levels of detail because of an incorrect choice of blending method. And lastly, we can see that the individual evaluation of their Glinty NDF is both expensive and unstable. We can observe rendering times that are highly variable when only changing the glint density. The goal of our work was to bring a solution to each of those fundamental problems, and to do so we built upon Zer and Kaplinen's framework using binomial laws. We resolved the problem of anisotropic pixel footprints at its source, thanks to a change of level of detail structure, and greatly reduced the base cost of the method. By bringing a new insight into the interpolation of binomial distributions, we solved the blending artifacts between levels of detail. And finally, by proposing a new way to approximate a draw of the binomial law in constant time, we greatly reduced the rendering time variability in all possible scenarios. So first, let's talk about anisotropy. Here we see again the level of detail structure used by Zer and Kaplinen, this time in real conditions. So for each vertex of the grid, we drew a number from a binomial distribution. The LOD method allows these glints to be both anchored on the surface while adapting to the scale of the pixel footprint, with the goal of sticking as close as possible to 1 pixel equals 1 texel on the grid. In practice, we need to evaluate and blend 2 grids per pixel, and for each grid, we need 4 binomial draws with bilinear interpolation to get a continuous signal along the surface. So in total, we need 8 binomial draws per pixel. This is still reasonable, but of course the footprint can also be anisotropic. And in that case, the only solution is to manually integrate the footprint with many more samples, just like hardware anisotropic filtering, but without hardware acceleration. In practice, they limit their methods to a max anisotropic factor of 16, as beyond that the cost really explodes, and it's sufficient to handle most real cases, but at what cost? With GPUs being highly parallelized, all it takes is 1 pixel with a high anisotropy to slow down an entire group of threads. And this is where the biggest performance problem of these two methods lies. We will try something else. We're back to our isotropic LOD structure, but this time the footprint doesn't grow isotropically, it stretches in one axis. So we can go back to 1 pixel equals 1 texel in this situation too. We add a second dimension to our LOD structure, which stretches the grids to compensate for the stretching of the footprint. In doing so, we've extended from a one-dimension scaling LOD blending space to a blending space in 2 dimensions, a scaling and a stretching, and we now just need to blend between 4 grids instead of 2. But what do we do when the footprint is anisotropic, but in the different direction? We keep applying the same logic. We simply add a 3rd dimension to our LOD blending space, but this time it's a rotational axis to deal with the footprint's rotation. But we can't actually just divide this axis in discrete identical steps. If our footprint is much less anisotropic, the underlying virtual microfacets seen by the footprint barely change at all when the footprint rotates, so we need much less rotational steps. And when the footprint is much more anisotropic, the microfacets within the footprint change at a very high frequency, so we need much more steps. So instead, we use an adaptive subdivision of the rotational axis, where we double the amounts of steps for every step in the stretching axis. Thanks to this, we now have something that behaves exactly how we want, a new LOD structure that can adapt to anisotropic pixel footprints and staying very close to 1 pixel equals 1 texel. But if we naively implement this new 3-dimension LOD blending space, we would actually have to be blending between 10 grids at once. And each grid requires 4 bilinear samples, so that's a lot. So instead, we'll do something better. If we look at the basic pattern of this blending space in the 2D stretching and rotation axis, we have a pentagon. But the most simple shape in 2 dimensions, the simplest shape, is the triangle. So let's triangulate this whole space. And now if we add back in the 3rd dimension, each of these triangles in 3D becomes a prism with a triangular base. And each of these prisms can be divided into exactly 3 tetrahedra, which is the 3D simplex shape. So now, by simply identifying within which tetrahedron our sampling point is located and finding its barocentric coordinates within it, we can evaluate our 3D LOD blending space with only 4 grids instead of 10. So in conclusion, our new LOD structure is twice as expensive as the previous one in the isotropic case, but vastly cheaper as soon as anisotropic kicks in. And its most important feature is that it's a constant time algorithm. We always need to evaluate only 4 grids with 4 texels each, whatever the pixel footprint is. And the cherry on top is that it can also handle any possible anisotropy factor, even above 16 and up to infinity, where the other methods simply cannot go. Now let's keep going with the second fundamental building block. Now that we have our 4 different grids to evaluate, we need to determine how to properly interpolate between them. Both previous methods do this interpolation linearly between the end results of the 2 grids, and that's simply where their blending artifacts come from. Linear interpolation doesn't preserve any statistic of the interpolated distributions, except for the mean, but in the case of glints, these statistics are very important. So how can we solve this? In our paper, we looked specifically into Zur and Kaplinen's framework using binomial distributions, and it so happens that in this framework, we can easily solve this issue. We introduced the concept of distributed binomial laws, which allow us to get the correct result in blue on the right, and I'll refer to the paper for more in-depth analysis, but the important thing to know is that in the end, it's a very small change to make. Instead of interpolating the outputs of the binomial draws, we interpolate the inputs and then add the results together. Intuitively, this approach simply turns the glints on or off progressively on each side. And thanks to this, we can completely eliminate the blending artifact issue within Zur and Kaplinen's framework. And finally, the last fundamental building block is the evaluation of the binomials themselves. How do we sample a binomial distribution in practice? Here we see the reference. To sample it, we need to chain together n Bernoulli trials of probability p, and this, of course, becomes impossible to do in real time when n becomes large. Instead, the common alternative is to approximate it with a Gaussian distribution. As we see here, when the parameters n and p of the binomial are large enough, the distribution becomes very close to a Gaussian. So what Zur and Kaplinen do is they compute the real binomial when n or p are small, and switch to a Gaussian when a chosen criteria is crossed. But this creates a hard visible seam in between the 2 regions, and it still implies manually looping a certain amount of Bernoulli trials before transitioning. And more importantly, it still means a variable amount of iterations. And as I've said before, on GPUs that's very bad. Here we've measured the variance in timings observed for a fixed scene when only changing the microfacet density parameter. We introduce a new binomial approximation to solve this issue. It evaluates in constant time on both sides with a continuous transition between the two, allowing us to drastically reduce the instability of the performance. Our approximation is pretty simple. We start with doing a single Bernoulli trial using the probability of having at least one success in the binomial. Separately, we also do a Gaussian approximation of the binomial law, but knowing that we already have one success, so we decrease n by 1 and add 1 to the result. And now if we multiply both, we get the gated Gaussian approximation of the binomial law in constant time. It correctly reproduces the stochastic behavior of the binomial law in the small numbers and converges to the same Gaussian distribution as the binomial law when n grows to infinity. And that's it. We've now seen how to bring key improvements to the 3 fundamental building blocks of these real-time glint rendering methods. Thanks to our anisotropic level of detail structure and thanks to our new binomial approximation, we get a very significant performance improvement in real scenes compared to previous methods. Here we've measured these timings on an RTX 2080 at 1080p, sorry. Additionally, this performance is now almost completely stable. Our paper also brings other improvements that I don't have the time to get into today. For example, thanks to our performance improvements, we can afford to have glints that appear and disappear smoothly, which Sir and Kaplinen couldn't do. Thanks to this, we can compare our method to that of Sherman and others, which we consider as the state-of-the-art result for real-time glints when it comes to quality, because of their physically based pre-calculated NDFs. And it turns out that even in our less physically based setup, with binomial glints, we can obtain results that are identical to theirs. And our other big improvement in the paper is a very simple NDF formulation which allows us to target any continuous NDF, including GGX, whereas both previous methods are limited to the Beckman NDF. This is what allowed us to integrate our method in Unity's high-definition render pipeline. So finally, we give, thank you. Finally, we give our complete source code for reimplementation, as well as the demo you just saw, and another benchmark demo where you can compare the 3 methods together. That's it. Thank you very much for your attention, and I'll be happy to answer a very little amount of questions.